100 trillion years from now, the last star in the universe will burn out. The hydrogen fuel that powered stellar fusion for eons will be exhausted. The star will cool, collapse, and fade into darkness. No new stars will form. The galaxies will be invisible, their constituent stars long dead, scattered as dark remnants drifting through the void. The universe will enter an era where light no longer exists, where temperature approaches absolute zero, where entropy has won. I gave an artificial intelligence a task that astrophysicists discuss in quiet voices. I fed it cosmological models, data from deep space observations, thermodynamic equations, and simulations of stellar evolution spanning trillions of years. I asked it to map out what happens when the last star dies. Not if, when. The answer is more detailed and more desolate than most people realize. Today we walk through the timeline from now until the heat death of the universe. We will look at what stellar death means, why stars cannot burn forever, and what remains when the cosmos goes dark. Stay with me. This is about the ultimate fate of everything. If you want analysis where AI examines the deepest questions about time, entropy, and the end of everything, subscribe to Mike AI Production now. This is where cosmology meets existential timescales that make human history invisible. To understand the death of the last star, we need to understand what stars are and how they die. A star is a ball of hydrogen gas compressed by its own gravity until the core reaches temperatures high enough for nuclear fusion. In the core of a star like our Sun, hydrogen nuclei collide with enough energy to overcome electromagnetic repulsion. They fuse into helium, releasing energy. This energy pushes outward, balancing the inward pull of gravity. The star remains stable. But fusion requires fuel. Hydrogen is finite. A star like the Sun will burn for approximately 10 billion years. Larger stars burn hotter and faster, exhausting their fuel in millions of years. Smaller stars, red dwarfs with a fraction of the Sun's mass, burn slowly and can last trillions of years. But eventually, every star runs out of hydrogen. When a star exhausts its hydrogen, what happens depends on its mass. Massive stars, those with more than 8 times the Sun's mass, fuse heavier elements in their cores after hydrogen is gone. Helium fuses into carbon and oxygen. Carbon fuses into neon, magnesium, silicon. Silicon fuses into iron. But iron cannot fuse and release energy. Fusing iron requires energy input rather than releasing it. The core, now iron, collapses catastrophically. The outer layers explode in a supernova. What remains is either a neutron star or a black hole. Medium-sized stars like the Sun do not explode. When the hydrogen in the core is gone, the core contracts and heats up. Hydrogen in a shell around the core begins to fuse. The outer layers expand dramatically. The Sun will become a red giant, swelling to engulf the inner planets, possibly including Earth. After millions of years as a red giant, the outer layers drift away, forming a planetary nebula. The core, no longer generating energy, collapses into a white dwarf. A white dwarf is a stellar remnant roughly the size of Earth, but with a mass comparable to the Sun. It is incredibly dense. A teaspoon of white dwarf material would weigh tons on Earth. The white dwarf is not fusing anything. It is simply cooling. It radiates residual heat into space. Over billions of years, it will cool until it becomes a black dwarf, a cold, dark object no longer emitting visible light. Small stars, red dwarfs, burn so slowly that none have yet reached the end of their lives. The universe is only 13.8 billion years old. Red dwarfs can burn for 100 trillion years or more. These are the stars that will be the last to die. When they do, they will follow the same process as the Sun. Their cores will collapse into white dwarfs. They will cool. They will go dark. The AI constructed a timeline. Let me walk you through the eras of the universe from now until the last star dies and beyond. Era 1, the stelliferous era. We are here, now. Stars are being born in nebulae, vast clouds of hydrogen gas and dust that collapse under their own gravity. The Orion Nebula, visible to the naked eye as a fuzzy patch in the constellation Orion, is a stellar nursery where hundreds of new stars are forming. Hot, young stars illuminate the gas around them, creating the beautiful, glowing clouds we see in telescope images. Star formation peaked approximately 10 billion years ago, when the universe was rich in hydrogen and galaxies were actively colliding and merging. These collisions compressed gas clouds, triggering bursts of star formation. Entire galaxies lit up with millions of massive blue stars burning through their fuel at prodigious rates. But those peak conditions are gone. The rate of new star formation has been declining for billions of years. Galaxies have settled into more stable configurations. The gas needed for stars has been consumed or dispersed by stellar winds in supernova explosions. Hydrogen clouds are thinner, less dense, less likely to collapse. But stars are still forming. In our Milky Way galaxy, approximately 7 new stars are born every year. Across the entire observable universe, the number is still in the millions per year. This era will last for another 10 trillion to 100 trillion years, depending on how you measure it. During this immense span, stars will continue to be born, live their lives, and die. But the rate of birth will continue its slow decline. Each generation of stars locks up hydrogen in stellar remnants that cannot participate in future star formation. White dwarfs, neutron stars, and black holes accumulate like cosmic debris, removing matter from the cycle. Massive stars, those with more than 8 times the sun's mass, have already mostly died. These stars burn hot and fast, exhausting their hydrogen in mere millions of years. They exploded as supernovae billions of years ago, leaving behind neutron stars and black holes. The stellar population is now dominated by medium-sized stars like the Sun and smaller red dwarfs. Around 1 trillion years from now, the last new stars will begin to form. The available hydrogen in galaxies will be nearly exhausted. The final stellar nurseries will collapse, creating one last generation of red dwarfs. These stars, with masses between 10 and 50% that of the Sun, will be the survivors. They burn slowly, conserving their fuel, able to maintain fusion for tens or hundreds of trillions of years. After this point, no new stars will be born. The gas and dust reservoirs are gone. Existing stars will continue to burn, but there will be no replacements. The universe enters a long twilight as stars die one by one, without successors. The first to go are the medium-sized stars. Our Sun, in approximately 5 billion years, will exhaust the hydrogen in its core. The core will contract and heat up. Hydrogen fusion will move to a shell around the core. The Sun will swell into a red giant, expanding to perhaps 100 times its current diameter. The inner planets, Mercury and Venus, will be engulfed. Earth may survive, pushed outward by the loss of the Sun's mass, or it may be consumed. Either way, Earth will be uninhabitable, its oceans boiled away, its atmosphere stripped, its surface molten. The Sun will remain a red giant for hundreds of millions of years. Then the outer layers will drift away, forming a planetary nebula, a glowing shell of gas expanding into space. What remains is the core, now exposed, a white dwarf about the size of Earth, but containing most of the Sun's original mass. This white dwarf will be incredibly hot initially, tens of thousands of degrees at the surface, but it will not be fusing anything. It will simply cool, radiating its residual heat into space. All medium-sized stars follow this path. Over the next trillion years, stars like the Sun will swell, shed their outer layers, and become white dwarfs. These white dwarfs are the stellar corpses of the stelliferous era. Era 2. The degenerate era, 100 trillion years from now. The last red dwarf stars, those tiny dim embers that have been burning since the early universe, are finally exhausting their hydrogen fuel. These stars lived frugally, fusing hydrogen at such slow rates that they could maintain themselves for tens of trillions of years. But even they cannot escape entropy. A red dwarf in its final days swells slightly, not dramatically like a larger star, but enough to shed some mass. The outer layers drift away. The core contracts into yet another white dwarf, smaller and cooler than those left by sun-like stars, but following the same thermodynamic fate. The universe now contains no active stars. No fusion is occurring anywhere. What remains are white dwarfs, neutron stars, black holes, and planets that have long since frozen solid. The temperature of space itself has dropped to approximately 3 Kelvin, only 3 degrees above absolute zero. The cosmic microwave background radiation, the afterglow of the Big Bang, has been redshifted by cosmic expansion to microwave and then radio wavelengths and beyond, contributing almost no heat. The galaxies still exist structurally, but they are invisible. If you could somehow stand on a planet in this era and look up, you would see absolute blackness. No stars, no nebulae, no galaxies. The nearest white dwarf might be 5 or 10 light years away, emitting so little light that it would be invisible to the naked eye, detectable only by its faint infrared radiation. The Milky Way, once a majestic spiral galaxy with hundreds of billions of stars, is now a dark collection of white dwarfs, neutron stars, and black holes, slowly drifting apart. Galaxies are no longer held together as tightly as they once were. Over trillions of years, gravitational interactions have ejected many stars from their galaxies entirely. These rogue stars, now dark remnants, wander the intergalactic void alone. Planets, if any remain attached to white dwarfs, are frozen wastelands. Their atmospheres, if they ever had any, have long since frozen solid and fallen to the surface as layers of nitrogen ice, carbon dioxide ice, even oxygen ice. The temperature on these worlds is a few Kelvin, just barely above the cosmic background. No liquid water exists anywhere. No chemical reactions occur at any appreciable rate. Any complex molecules have long since broken apart from cosmic ray bombardment over trillions of years. White dwarfs cool slowly. They radiate heat through thermal radiation, but they generate no new energy. The cooling process takes trillions of years. Initially, a white dwarf is hot enough to glow white or blue-white, tens of thousands of degrees. Over billions of years, it cools to yellow, then red, then infrared. After tens of trillions of years, it reaches the temperature of the cosmic background. At this point, it becomes a black dwarf, no longer emitting any detectable radiation. Black dwarfs are theoretical objects. The universe is not old enough for any to exist yet. The oldest white dwarfs, formed from the first generation of stars billions of years ago, are still cooling. But in the degenerate era, black dwarfs are the dominant remnant. Cold, dark, inert spheres of carbon and oxygen. They drift through space, monuments to stars that died eons ago. But even black dwarfs are not permanent. Protons, the particles that make up atomic nuclei, may not be stable forever. The standard model of particle physics does not predict proton decay, but some grand unified theories suggest that protons have a finite lifespan, perhaps 10 to the 34 years. If protons decay, then atoms themselves eventually disintegrate. A black dwarf made of carbon and oxygen atoms will slowly evaporate as protons decay one by one. Each decay releases a small amount of energy, a positron and other particles. Over unimaginable timescales, the entire black dwarf dissipates into a diffuse cloud of electrons, positrons, neutrinos, and photons. Planets undergo the same fate. A frozen world orbiting a black dwarf, its surface covered in layers of ice and rock, will slowly disintegrate particle by particle. The silicon atoms in the rock, the oxygen atoms in the ice, the iron in the core, all decay. The planet becomes less solid, less coherent, until it is no longer a planet, but a dispersing cloud of elementary particles. The timescale for this is approximately 10 to the 40 years. If you lived in this era, which you cannot, and you watched a planet decay, it would appear unchanging for billions upon billions of years. Then, gradually, the surface would become less solid, the edges less defined, the structure less organized, until it faded into invisibility. Era 3, the black hole era, 10 to the 40 years from now. If proton decay has occurred as predicted, the universe is now devoid of ordinary matter. No atoms, no molecules, no white dwarfs or planets or dust. What remains are black holes, the only objects still held together by gravity rather than electromagnetic forces. These black holes form from the cores of massive stars that exploded as supernovae billions or trillions of years ago. At the time of their formation, they were modest, perhaps 3 to 100 times the mass of the Sun. But over the immense spans of time, they have grown. Black holes near the centers of old galaxies have merged with each other, combining mass. They have swallowed the occasional stray particle or photon that wandered too close. Supermassive black holes, those that once sat at the centers of galaxies with masses of millions or billions of suns, are now the titans of the cosmos. But even these are small compared to the emptiness surrounding them. Space has expanded so much that the distance between black holes is measured not in light years, but in millions or billions of light years. Each black hole is effectively alone, isolated, with no companion, no nearby matter, nothing but the void. Black holes are not eternal. Stephen Hawking discovered in the 1970s that black holes emit radiation due to quantum effects near the event horizon. Virtual particle pairs, a particle and an antiparticle, spontaneously form from the vacuum. Normally, they annihilate each other almost instantly, but near the event horizon of a black hole, one particle can fall in while the other escapes. The escaping particle is real radiation. The black hole loses a tiny amount of mass energy to produce it. This Hawking radiation is extraordinarily weak for large black holes. A black hole with the mass of the Sun has an event horizon temperature of approximately 60 nanokelvins, far colder than the current cosmic background. It absorbs more radiation from the background than it emits. But as the universe expands and cools, the background temperature drops below the Hawking temperature. At that point, the black hole begins to lose mass, slowly at first, then accelerating as it shrinks. The evaporation time for a black hole scales with the cube of its mass. Giga-mass black hole would take approximately 10 to the 67 years to evaporate completely. The calculation is straightforward, but the result is staggering. 10 to the 67 is a number with 67 zeros after the 1. It is a timescale so long that comparing it to the current age of the universe, 13.8 billion years, is like comparing a second to the age of the universe. Supermassive black holes take even longer. A black hole with 1 billion solar masses, like the one at the center of the Milky Way, would take approximately 10 to the 98 years to evaporate. A black hole with 1 trillion solar masses, if such a thing exists, would take 10 to the 104 years. During the black hole era, these objects evaporate one by one. Smaller black holes go first. They shrink, their Hawking temperature rises, the radiation intensifies. In the final moments before a black hole vanishes, it undergoes a rapid evaporation. The Hawking temperature spikes to billions or trillions of degrees. The black hole emits a burst of high-energy particles and photons, a final flash of light in the dark universe. Then it is gone, leaving nothing but expanding radiation. Larger black holes take longer. They evaporate more slowly, maintaining lower temperatures. But eventually, every black hole, no matter how massive, reaches its end. The last supermassive black hole, perhaps one that was 1 trillion solar masses and sat at the center of a massive galaxy cluster, will evaporate around 10 to the 100 years from now, give or take a few orders of magnitude. When this final black hole emits its last photon and disappears, nothing remains but radiation. The universe transitions to the next era. Era 4, the Dark Era, 10 to the 100 years and beyond. The last black hole has evaporated. The universe is now a diffuse, nearly uniform sea of photons, neutrinos, electrons, positrons, and possibly other exotic particles predicted by theories beyond the standard model. The temperature is effectively zero. Not zero in an absolute sense, because quantum fluctuations prevent true zero, but zero in any practical sense. The average energy per particle is infinitesimal. If you could measure the temperature of space, it would be 10 to the minus many Kelvin, a number so small that it has no physical meaning. Entropy has reached its maximum. The second law of thermodynamics states that entropy always increases in a closed system. The universe is a closed system. Over the trillions upon trillions of years since the Big Bang, entropy has been climbing. Stars formed, burned, and died, converting ordered nuclear fuel into disordered heat and radiation. Black holes evaporated, releasing their organized mass energy as random photons. Now the process is complete. No gradients remain, no hot spots and cold spots, no dense regions and sparse regions. Everything is uniform. This uniformity is the definition of maximum entropy. In thermodynamics, entropy is a measure of disorder, or the number of possible microstates corresponding to a macrostate. A low entropy state is highly ordered. A high entropy state is highly disordered. The early universe, seconds after the Big Bang, was in a low entropy state. It was hot and dense, but uniform and simple. As the universe expanded and cooled, stars formed, creating pockets of low entropy locally, but increasing the total entropy of the universe. Now, in the dark era, the universe has reached equilibrium. No further change is possible that would increase entropy. Without energy gradients, no work can be done. Life, computation, thought, all require the ability to harness energy differences. You cannot power a machine or a brain without a hot reservoir and a cold reservoir. In the dark era, everything is the same temperature. There are no reservoirs. There is nothing to power anything. Space continues to expand, driven by dark energy. The expansion is accelerating, as it has been for the past few billion years in our current era. Regions of space that were once part of the same galaxy, or even the same galaxy cluster, are now separated by distances so vast that light from one can never reach the other. The observable universe from any given point shrinks. If you were somehow a conscious observer in this era, an impossibility, but imagine it anyway, you would see nothing. The nearest photon might be 1 billion light years away. The next might be 1 billion more beyond that. You would be profoundly alone, unable to interact with anything, unable even to detect that anything else exists. The universe from your perspective would be indistinguishable from a void. Some cosmologists speculate about processes that might occur on timescales beyond 10 to the 100 years. Quantum mechanics allows for fluctuations, temporary violations of energy conservation, where particles spontaneously appear and disappear. Most of these fluctuations are tiny and brief. But given infinite time, rare events become inevitable. A quantum fluctuation might assemble particles into a structure. If the fluctuation is large enough and arranged correctly, it could create something complex: a star, a planet, a brain. These are called Boltzmann brains, hypothetical observers that arise spontaneously from thermal fluctuations in a high-entropy state. The probability of a Boltzmann brain forming is extraordinarily low. But in an infinite amount of time, low probability events occur. In fact, they occur infinitely many times. This leads to a paradox. If the universe exists for an infinite amount of time and Boltzmann brains form, then the vast majority of observers in the universe are Boltzmann brains, not evolved creatures like us. But Boltzmann brains have random memories and perceptions. They are far more likely to experience sensory chaos than coherent reality. Yet we experience coherent reality. This suggests either that the universe will not last forever, or that our assumptions about Boltzmann brains are wrong, or that we live in a simulation or some other exotic scenario. The AI flagged this as an open question in cosmology. The Boltzmann brain paradox is not solved. It is a consequence of taking the heat-death scenario to its logical extreme with infinite time. The AI noted that this timeline assumes the universe continues to expand forever, driven by dark energy. This is the current best model based on observations, but there are alternative scenarios. If dark energy weakens or reverses, the expansion could slow and eventually reverse. The universe would begin to contract. Galaxies would move toward each other instead of apart. Eventually, everything would collapse back into a singularity, a big crunch, the opposite of the Big Bang. In this scenario, the universe does not die from cold and entropy, but from heat and compression. Stars would be ripped apart as galaxies collide. Matter would be crushed to infinite density. Then, possibly, a new Big Bang, a cyclic universe. Another scenario involves vacuum decay. The universe might be in a metastable state, like a ball resting in a shallow valley. It is stable for now, but a quantum fluctuation could push it over the edge into a lower energy state. If this happens, a bubble of true vacuum would form and expand at the speed of light, annihilating everything in its path. The laws of physics inside the bubble would be different. Atoms as we know them could not exist. This could happen at any moment or never. We have no way to predict it. But the most likely scenario based on current evidence is the heat death. The universe expands forever. Stars die, black holes evaporate. Everything cools to equilibrium. The end is not a bang but a fade. What does this mean for humanity or any intelligent life? The AI evaluated the timescales and the possibilities for survival. Humanity has existed in recognizable form for approximately 300,000 years. Anatomically modern humans emerged in Africa and spread across the world. Civilization, with agriculture and cities and writing, has existed for roughly 10,000 years. Industrial civilization is only a few hundred years old. From this perspective, the lifespan of stars, measured in trillions of years, seems infinite, but it is not. The sun will exhaust its hydrogen in approximately 5 billion years. Long before that, perhaps in 1 billion years, the sun's gradually increasing luminosity will make Earth uninhabitable. The oceans will evaporate, the atmosphere will be stripped away by solar wind. Earth will become a sterile rock orbiting a brightening star. If humanity survives this, it must move, either to another planet in the solar system, like Mars or the moons of Jupiter, or to another star system entirely. Interstellar travel is technically challenging, but not impossible. Generation ships, where populations live and die over centuries-long voyages, are conceptually feasible. Cryogenic sleep, if the technology can be developed, would allow travelers to survive the journey. Self-replicating probes could seed other star systems with human DNA and instructions to grow new humans, a form of digital resurrection. Even if humanity spreads to other stars, the timeline is still finite. Stars die. If a civilization wants to survive the end of natural star formation, it must adapt to an environment where stellar energy is no longer available. This requires finding alternative energy sources that can sustain complexity and consciousness for trillions of years. One proposal is to harvest energy from the rotational energy of black holes. The Penrose process, named after physicist Roger Penrose, describes a method for extracting energy from a rotating black hole. The black hole's spin creates an ergosphere, a region outside the event horizon where space-time itself is dragged around the black hole. An object entering the ergosphere can split, sending part of itself into the black hole, while the other part escapes with more energy than it entered with. The black hole loses rotational energy. The escaping object gains it. A sufficiently advanced civilization could build structures around black holes to harness this energy. Ring worlds or Dyson spheres, megastructures that encircle the black hole and extract energy from infalling matter, or the ergosphere. The energy output could power a civilization for millions or billions of years, as long as the black hole has rotational energy to give. But this strategy has limits. Black holes eventually stop spinning. The energy is finite. And as the universe expands, black holes become more isolated. Reaching another black hole to exploit after exhausting the first becomes increasingly difficult. Another proposal is to use energy from Hawking radiation. As black holes evaporate, they emit particles and photons. A civilization could capture this radiation and convert it into usable energy, but the power output is minuscule. A solar mass black hole emits approximately 10 to the negative 28 watts. That is far less than a single light bulb. To power a civilization, even a minimal one, you would need millions or billions of black holes, and they would need to be clustered close enough to harvest. There is also the problem of timescale. Hawking radiation becomes significant only in the final stages of a black hole's evaporation, when it is small and hot. But waiting for a supermassive black hole to shrink to a harvestable size takes 10 to the 98 years or more. No structure, no computer, no consciousness built from matter, as we understand it, could survive that long without external energy. Some physicists have speculated about reversing entropy locally. Life, in a sense, already does this. Living organisms are highly ordered systems. A human body is more organized than the food and air it consumes. But this local decrease in entropy is paid for by increasing entropy in the environment. You exhale carbon dioxide, a more disordered molecule than the glucose you metabolized. You radiate waste heat. The total entropy of the system, including you and your environment, increases. Could an advanced civilization do this on a cosmic scale? Create pockets of low entropy, regions where complexity and order persist, while increasing entropy elsewhere to compensate. The second law of thermodynamics says that the total entropy of a closed system always increases. The universe as a whole is a closed system. Any local decrease must be matched by a greater increase elsewhere. A civilization attempting this faces diminishing returns. As the universe approaches maximum entropy, the cost of creating order becomes prohibitive. You need more and more energy to maintain less and less complexity. Eventually, the energy required exceeds the energy available. The battle against entropy is lost. The AI concluded that long-term survival past the heat death is implausible under known physics. The second law of thermodynamics is not just a guideline, it is a fundamental constraint. Entropy always increases. Energy disperses. Complexity breaks down. Whatever exists in the dark era, if anything, will not resemble life or thought as we know them. But there are speculative, highly theoretical ideas that push beyond known physics. Some suggest that consciousness might exist in forms we do not currently understand or detect. Perhaps patterns in quantum fluctuations, operating on timescales of trillions of years, could support something analogous to thought. Perhaps information itself, independent of any physical substrate, persists in ways we cannot yet measure. These ideas are closer to philosophy than physics. They require postulating new laws or new interpretations of existing laws. There is no evidence for them, only the conceptual possibility. But in the face of heat death, speculation is all that remains. Another speculative idea involves creating new universes. Some interpretations of quantum mechanics and general relativity suggest that it might be possible to engineer a new Big Bang, creating a baby universe that buds off from our own. This new universe would have its own space-time, its own physics, potentially its own stars and galaxies and life. An advanced civilization, facing the heat death of its own universe, might attempt this as a legacy project. They cannot save themselves, but they can seed a new cosmos. They could even, in principle, encode information into the initial conditions of the new universe, influencing its physical constants and laws to make it hospitable to life. This would not be survival, but it would be continuation. Intelligence would persist in a new form, in a new universe. The physics of creating baby universes is speculative and unproven. It requires manipulating quantum fields or black holes in ways we do not know how to do and may not be possible. But some models suggest it is not forbidden by the laws of physics as we currently understand them. It is merely far beyond our technology. Finally, there is the possibility that our understanding of the universe is incomplete. The history of physics is a history of paradigm shifts. Newtonian mechanics was overturned by relativity and quantum mechanics. The absolute space and time of Newton gave way to the space-time of Einstein. Determinism gave way to quantum uncertainty. Perhaps there will be another revolution. Perhaps future discoveries will reveal new principles that allow circumventing entropy or tapping into energy sources we cannot currently imagine. Perhaps the heat death is not inevitable, but contingent on assumptions that will turn out to be wrong. This is not wishful thinking disguised as science. It is an acknowledgement that science progresses by discovering the limits of existing theories and building new ones. We do not know what we do not know. The heat death is the prediction of our best current models. But models change. Let me give you 3 conclusions. Pick the one that resonates. Conclusion for the nihilist. The heat death of the universe is inevitable. Stars will die. Black holes will evaporate. Everything ends in cold, dark, maximum entropy. Life is a temporary aberration in a cosmos trending toward disorder. Meaning, purpose, consciousness, these are flickering sparks in an indifferent void. They will go out. Nothing we do matters on cosmic timescales. Embrace the absurdity. Enjoy the spark while it lasts, knowing it is finite and ultimately meaningless. Conclusion for the pragmatist. The heat death is real, but unimaginably distant. 100 trillion years is so far in the future that worrying about it now is pointless. Humanity might not survive the next century, let alone trillions of years. Focus on the challenges we face now. Climate change, nuclear war, inequality. These are immediate and solvable. The fate of the last star is a problem for civilizations trillions of years more advanced than us, if they exist. Our responsibility is to survive the next few hundred years and build a foundation for whatever comes next. Conclusion for the optimist. The heat death is based on our current understanding of physics. But physics has been revolutionized before. Newtonian mechanics gave way to relativity and quantum theory. Perhaps future discoveries will reveal ways to circumvent entropy or tap into energy sources we cannot yet imagine. Perhaps consciousness can exist in forms beyond matter and energy. Perhaps the end of this universe is the beginning of something else. The universe has surprised us before. It will surprise us again. Hope is not irrational. It is a bet on the unknown. As for me, I find the pragmatist position most defensible. The heat death is real and supported by our best models, but it is so distant that it holds no practical relevance to human concerns. The sun will die long before the last star. Earth will be uninhabitable long before the sun dies. Our survival depends on solving problems measured in decades and centuries, not trillions of years. The fate of the last star is fascinating, but it is not urgent. If this video changed how you think about time, entropy, and the ultimate fate of everything, that is the goal. Cosmology is not just about distant stars. It is about understanding the framework in which everything exists, including us. Subscribe to Mike AI Production for more investigations where AI examines questions on timescales that make human history invisible. Hit like if you want more content on the deep future and the end of the universe. Leave a comment. Tell me, does the heat death depress you or liberate you from worrying about legacy? I read every response. Thanks for watching. See you in the next one.